Thank you for watching my presentation. My name is Dohyeon Lee, currently a research associate at UC Santa Cruz. I'm going to talk about the declining entry rate and productivity growth. Recently, several papers have expressed concerns about the declining entry rate in the US as well as in other advanced economies. In addition, there has been a slowdown in productivity growth in almost all advanced economies. This paper proposes a novel explanation for the decline of both the entry rate and productivity growth. Here are some motivating evidence. The solid black line is the entry rate in the US, and the red dashed line is the employment share of new firms. The entry rate is the number of new firms with age less than 1 year, divided by the number of existing firms last year. We can see clear downward trends in both of these series. This figure shows the annual growth of labor productivity per hours in advanced economies, including the US, Euro areas, UK, and Japan. In this figure, we are capturing the long-run cycles as opposed to business cycles. With the exception of the US around 1990s, we can see clear downward trends of productivity growth in almost all advanced economies. Now here's a summary of what I do. I propose a simple and general framework for firm and industry dynamics that can achieve a fair comparison between incumbents and entrants. And I will show why the stationary models cannot achieve such a fair comparison. The model features a declining entry rate in the absence of shocks, which in turn leads to the productivity slowdown on the extensive margin. Because the entry rate may not be a good measure of entry, I propose an alternative measure that would be constant in the normal state. I estimate this entry index using the employment share of firms by entry cohort relative to some fixed initial cohort. I also studied the implication of declining population growth, one of the leading explanations in the recent literature on the declining entry rate. Here is a summary of the related literature. There are papers that document and explain the declining entry rate as well as productivity slowdown. In addition, there are also papers that explain other secular trends in other macroeconomic variables. The current paper explains why the decline in both the entry rate and productivity growth can occur in the normal state. This is a distinctive feature because pretty much all the literature uses some exogenous force to explain these trends. So this paper acts to complement the existing studies in an important way. In addition, there are big literatures on each of the following subjects: economic growth and ideas, firm dynamics, and creative destruction, as well as industry life cycle. The current paper proposes a simple and general framework that encompasses all these literatures. Here is the outline of the presentation. First, I will summarize the model mechanism and discuss the implications of stationarity. Second, I will give a brief overview of the model. Third, I will explain the quantitative exercise that I do. Let me begin by the model environment. The population is divided into workers and entrepreneurs with an elastic labor supply. Running a business as an entrepreneur requires an idea, and the quality of an idea serves as the productivity for producing that good. In the beginning of each period, some workers find new ideas. There is an exogenous arrival of ideas which are drawn from some given distribution. Once found, an idea remains permanently at that initial quality. After the ideas are found, occupation choices are made. Entry is the transition from worker to entrepreneur, and this occurs if the new idea is better than the current threshold. Exit is the transition in the opposite way, and this occurs if the previously owned idea becomes inferior to the current threshold. Because there is no cost of entry or exit, the threshold for both entry and exit coincide. And at this common threshold, profit is equal to the wage. Production combines the entrepreneur's idea with the worker's labor input, which is homogeneous. And the standard monopolistic competition with CES demand leads to the constant markup rule for the entrepreneurs. Now let me explain the mechanism. The entry rate can be expressed as the product of the rate of finding new ideas and the probability that the idea is above the current threshold. As ideas accumulate over time, the threshold idea, AT star, must rise in equilibrium. And why is that? Here, exit is positive only if there is a rise in the threshold. Suppose the threshold doesn't change while there is positive entry. Then there is entry, but no exit. So labor demand increases and labor supply decreases. This leads to a higher wages and lower profit, and therefore the least productive firms are driven out of the market. In other words, positive entry implies positive exit, and therefore a rise in the threshold. Now, if the distribution of new ideas is time invariant, the probability that an idea is above the threshold must decrease over time. And this is already sufficient to generate a declining entry rate. The story was pretty simple, and you might wonder, is this really a novel story? The key to this story is that ideas accumulate without depreciation, and this story cannot be captured if stationarity is imposed. Under stationarity, something has to be done to keep this probability term constant over time. The workhorse models of firm dynamics feature stationarity in the joint distribution of the firm's productivity and age. In the next few slides, I will further elaborate on this point using examples. Let's first consider the case where the entrance distribution is fixed under stationarity. Stationarity implies that the threshold is constant to keep the entry rate constant. In this case, the incumbent firm's distribution needs to deteriorate over time to make room for the same mass of entrants each period. For example, in Hohenheim, mean reversion among survivors implicitly plays this role. This figure shows the firm's productivity distribution by ages stacked on top of each other. The top area corresponds to the new entrants, and they move down to the lower levels in each period. The difference between the adjacent areas correspond to the mass of firms that exit among the same cohort. In this example, the average productivity is the same across all ages and cohorts. However, this is conditional on survival. If we include the exiting firms with productivity below the threshold, such as this light area, the average productivity of a cohort must be decreasing over time. In other words, there are some built-in disadvantages imposed in the incumbent firms, and this occurs while the entrance distribution is fixed. As a result, we cannot really do a fair comparison between incumbents and entrants in this class of models. The other benchmark under stationarity would be where the incumbent's distribution is fixed. In this case, the entrance distribution needs to improve in each period to sustain stationarity. Again, we cannot do a fair comparison between incumbents and entrants. Finally, consider the case where both incumbents and entrants distributions are fixed. The ideas are drawn from the same distribution in each period, and they keep accumulating without depreciation. Then we will end up having an arithmetic growth in the measure of ideas, where only the upper tail is used by the entrepreneurs. Obviously, the distribution is not stationary in age because the share of each cohort would be something like 1/t, which is decreasing over time. The key takeaway is that if we want to do a fair comparison between incumbents and entrants, we should not be imposing stationarity. Now, let me move on to the null hypothesis, or the normal state, implied by the two benchmark models that we have seen, stationary and non-stationary. In the stationary null, there are built-in disadvantages on incumbents relative to entrants. Entry is as easy as always because incumbents deteriorate by themselves. An example would be the vintage capital, where newer capital is better, but it is costly for the incumbents to use new capital. Alternatively, the consumer's taste changes rapidly, and the incumbents cannot adapt to this as well as the entrants. In this economy, a decline of entry rate correctly reflects the decline in the entrance performance. In the non-stationary null, we impose the same starting line for both incumbents and entrants. Finding ideas is as easy as always, but it becomes harder to find profitable ideas over time because ideas or incumbents accumulate without depreciation. In this economy, a decline of entry rate occurs in the normal state, so it does not necessarily reflect a decline in the entrant's actual performance. So what are the reasons to prefer the non-stationary null? At the bottom line, regardless of how the data looks like, non-stationary null would correctly measure the relative performance between entrants and incumbents. Using the non-stationary null, we can measure and analyze the incumbent firm's advantages over the entrants, which may be due to many reasons, including R&D, learning by doing, as well as preemption of the customer base. In addition, to my knowledge, stationary models of firm dynamics have been typically used in the aggregate, but less so at the industry level, which is often non-stationary. In a sense, my model opens up the possibility to use the firm dynamics model to study industry life cycles. Lastly, at least in the US, the aggregate level data is close to non-stationary null, as we will see later. A useful measure of entry should be kept constant in the normal state. Under the non-stationary null, the entry rate declines in the normal state because the denominator contains all the previous cohorts up to the last period. And this would be resolved if we fix some initial cohort and take it as the denominator. This is the basis for the entry index that I introduced in this paper. Now let me move on to the model overview. I will assume that both the entrance and incumbent distributions evolve exogenously over time. The entrance distribution H of A improves at rate zeta t between t minus 1 and t. This equation is just a simple transformation of random variables across period. In addition, all incumbent firms improve at rate gamma t between t minus 1 and t. Then the incumbent distribution G of A is governed by the following law of motion. The first term shows the improvement of all existing firms by gamma t, and the second term is the addition of new entrants. M is the mass of entrepreneurs, L is the mass of workers who can potentially find new ideas, and eta is the probability of finding an idea. And this equation holds above the current threshold, AT star. Combining the law of motion and the initial conditions, we can now solve for the current distribution of ideas in any period. We can simply add up the current distribution of each entry cohort and only take the upper tail above the current threshold AT star, which is to be determined endogenously. I assume Pareto distribution for the entrance distribution as well as the distribution of the initial cohort. Pareto is preserved under the above transformation, which greatly simplifies the analysis. The current distribution of ideas can be expressed as the product of three terms: the initial distribution, the growth of the initial cohort, and the sum of these components coming from each entry cohort normalized by the initial cohort, where this one indicates the share of the initial cohort itself. I define each of these relative components as the entry index. It measures the current share of cohort K relative to the initial cohort, and it is constant over time in the current environment. It is derived from the relative speed of improvement of the entrant relative to the incumbent in a cumulative way. The cumulative sum of the entry index is denoted by capital E, and I call this maturity index. We can now solve for the equilibrium threshold AT star by integrating this distribution above AT star and simply equating to M. Then AT star is proportional to the maturity index to the power of 1 over theta, and this captures the growth on the extensive margin, which is due to entry and exit. The other term, e to the gamma t, is the growth on the intensive margin, which is due to the incumbent firm's growth. And the average productivity is also proportional to this threshold productivity. Let me now explain how the null cases that I explained earlier would fit into this model. First, the non-stationary null is where the incumbents and entrants improve at the same rate. So the zetas are equal to gammas in all periods. Then the entry index would be constant over time, and the maturity index would exhibit an arithmetic growth. This is why the growth rate of productivity would decline over time, at least on the extensive margin. Next, the stationary null is where the entrants improve faster than the incumbents by a constant difference denoted by delta. The cumulative difference would then be proportional to the time t. The entry index would be growing at a constant rate, and in the limit, the maturity index would exhibit a geometric growth. Therefore, regardless of the initial condition, the economy would converge to a balanced growth path. Now let me move on to the quantitative exercise. To construct the entry index, I use the relative share of employment of firms by entry cohort. That is, the employment share of cohort K in period T divided by the share of initial cohort in the same period. Based on this simple model, this value should be constant over time. However, in the data, the relative share of employment typically declines over time as each cohort K becomes older. For example, if there is learning about one's own productivity or demand, the employment share would be initially higher and then gradually decline over time. In a reduced form way, I allow for the dependence of this variable on the current age of the cohort, which is T minus K. I call this function the age effect. Now let me explain how I jointly estimate the entry index and the age effect. Taking logs to this equation and then allowing for an additive error term, I can simply regress log of the relative share of employment non-parametrically on the entry year K and age is T minus K for each cohort K at each point in time T. I take a fifth order polynomial approximation for the log of the entry index and age effect. As a normalization, the age effect is set equal to 1 above the age of 20. Due to a few additional complications, I do non-linear least squares instead of OLS. These figures are directly from the BDS data, and they serve as the main ingredient to the estimation. The left panel shows the employment share by the firm's age groups. The dashed red lines indicate the stationary benchmark. That is, if the distribution is stationary in ages, these employment shares by age should be constant over time. But the data says that this is not the case. The right panel contains exactly the same information, but instead shows the maturity index by normalizing by the initial cohort. And then it is further decomposed into the entry index from each cohort. The distance between each pair of lines corresponds to the entry index. And the slope of these lines correspond to the age effect. Now here is the main estimation result. The top panel is the entry index, and the bottom panel is the age effect. The entry index was first increasing and then decreasing, but if I take a linear fit, the slope is very close to 0. So the US economy has been close to the non-stationary null, where incumbents and entrants grow at the same rate. The age effect is monotonically decreasing up to the age of 20. In this figure, the solid black line is the same entry index, and the dashed black line is the productivity growth on the extensive margin as implied by the model. Because the data is close to the non-stationary null, the maturity index has been growing linearly over time, and therefore contributed to the productivity slowdown on the extensive margin. Now let me move on to the effect of population. With population growth, the model predicts that the entry index is now multiplied by the level of the current population, simply because a larger population would find more ideas. Therefore, to capture the relative performance between incumbents and entrants, we need to divide the entry index by the current population. I call this population adjusted entry index. The solid black line is the same entry index, and the dashed black line is the population adjusted entry index, which is declining over time. The population growth has declined, but the level is still increasing, and therefore contributed to a faster improvement of the entrance. And that means the observed entry index was sustained only by an increasing population. So without population growth, the entry index would have declined, which means that incumbents were improving at a faster rate than potential entrants. Now let me conclude. The non-stationary null is useful because it allows for a fair comparison between incumbents and entrants, which was not possible under stationarity. Under the non-stationary null, entry rate declines and entry index is constant. Arithmetic growth implies that the rate of productivity growth declines on the extensive margin. The US data is close to the non-stationary null, but considering the population growth, incumbents have been improving at a faster rate than potential entrants, which is the opposite of the stationary null. I emphasize that this is a novel framework that can be used to study industry dynamics in general, which is often highly non-stationary. And that's it. Thank you very much for your attention.